Hello everyone, my name is Leo Burtscher. I'm a staff scientist at Leiden Observatory in the Netherlands and work mostly on METIS, the mid-infrared imager and spectrograph at the ELT, and on high-resolution studies of active galactic nuclei. But today I would like to talk about the climate crisis that we all know about, but where astronomy, I think, can be part of the solution if we want. So first, let's have a look at the problem. And for that, I think the best way is to look at the global carbon bucket, or the global carbon budget, here displayed as a bucket. That is, when the bucket is full, we have as much CO2 in the atmosphere as is needed to heat up the atmosphere by 1.5 degrees Celsius compared to pre-industrial levels, so that's around 1850. And this particular number, 1.5 degrees Celsius, with some extrapolation perhaps up to 2 degrees Celsius, has been identified as a more or less safe way that is still acceptable, let's say, that the Earth would not receive major damage from climate catastrophes at these temperatures. But we see already now with droughts and fires increasing everywhere that, and we're at about 1.2 degrees warming at the moment, that this is certainly not a number that is that can be treated lightly. So let's have a look at for a moment at this animation, and you can see how quickly it is filling up right now at this moment. Every day, every second, it is filling up. And you can also see the number here, perhaps in the end, that says that we have less than 10 years left to significantly do something about this. Otherwise, the bucket will be full and then it will start to overfill. That means we will exceed these 1.5 degree warming, certainly in the long term, and that will probably cause major problems that we do not want to, that we certainly do not want to bet about. The next graph shows this in a more linear form, and it shows how dramatically we have to reduce our emissions in order to still be compatible with this global carbon budget. Now, what does this all have to do with astronomers? I think there are two main ideas that astronomers can contribute to this problem, and perhaps actions that astronomers can do to become part of the solution of this problem. Number one is that we can have a look at our own carbon budget, at our own carbon emissions, our own carbon footprint. These are all the terminology that is used in this field. And this carbon footprint is rather large for most astronomers because we take part in international meetings, we compute on supercomputers and observe at remote sites, and all of these activities produce a lot of carbon emissions because most of our energy still comes from fossil fuels. So that is one point that we need to address, and I'm going to show a few examples about this in a minute. Another point that is perhaps equally important, because that can multiply the effect to many more people and not just our small discipline, is we can convey a feeling of how special our planet is and give this global, this astronomical picture, this astronomical view towards the Earth as a pale blue dot, as Carl Sagan said it a long time ago, based on the Voyager 1 picture. And this realization might even have more effect than our own than reducing our own carbon budget. But I think we have to do the first one, reducing our own carbon budget, in order to become credible actors when talking about the public. We cannot keep traveling around the world like crazy and then tell other people, oh, you need to reduce your carbon budget, or we should stop burning fossil fuels. That just is not very plausible then. There's of course many more things we can do. For example, we can join climate activists and give them scientific backing, tell them that when they have a sign that says there is no planet B, that they're actually right, that we actually know this from our own research. We can also ask universities to divest, to no longer invest in fossil fuel companies, and many more things of course. But the first 2 points, in my view, are most directly connected to astronomy, which is why I want to spend a few more slides on these two. So let's first talk about our own carbon footprint. I brought 3 examples here that I think are quite typical for various astronomical activities. The first one is a analysis that has been done by Knut Janke, that's going to be published in Nature Astronomy in September, in the September issue, about the carbon footprint of the MPAA, the Max Planck Institute for Astronomy in Heidelberg. And as you can see from the table, there are a number of contributors that have been taken into account, including electricity for lighting, for light production in the house. That includes supercomputing, includes meals, but also flights and even car travel to the institute. It does not include a few other things like hotel stays at other places, but they believe, and I think they are right in this, that the major contributors have been included. And as you can see, electricity production, which is required for supercomputing out of the house, but also for for running computers and servers in the house, is a major factor, as are flights. So these are the two big blocks that need to be addressed. For the first, it seems to be relatively easy how this can be addressed, namely by adding solar panels, for example, which MPAA is actually now doing on their roofs. That would already take away a lot of the load, because most of the load is happening during daytime, certainly for when people are actually there and working. For the flights, it is a bit less clear how this can be reduced, at least totally reduced, but we're going to get to this in a minute. Some more numbers here that are quite interesting to compare. So the total emissions correspond to something like 9 tons of CO2 equivalent per year per employee for work-related emissions alone. And now you might wonder, how does this compare to other emissions, to other countries? Well, I think the best comparison in this case is if you compare this to the average German citizen, they require 11 tons or produce 11 tons of CO2 emissions over a year for everything else. So by being an astronomer, you essentially double your carbon footprint compared to a person who is doing nothing, so to say, or perhaps even doing something less climate intensive, like being a teacher. That's one number to compare to. The other number that is interesting to compare to is to compare it to the per capita emissions in developing countries. For example, here's the 1.6 tons per capita in India, and that says that being an astronomer adds 6 times the amount of what an Indian person emits per year. So that gives perhaps a little bit of an impression of how much that actually is. The second example I'd like to bring is from ESO, who have done a carbon audit of all of their operations in 2018 by a professional company, Carbon 4. This is not yet fully published, but these few view graphs can be shown. And this does not include ALMA, in case you wonder, but it does include the VLT and La Silla operations. It does include the sites in Garching and in Santiago. And you can see that the split of emissions is quite a bit different to MPAA. It's, of course, ESO's main objective, of course, is to provide services to the community, to be the observatory and not so much to do the research themselves. So their main parts here are energy for powering the telescopes, and purchases. And the way this is all computed with how many emissions are generated upstream of the facility itself and how many emissions are produced after the product is produced, so to say, not so much an issue at ESO, is actually a quite complicated way of putting this all together. And I would urge you to look at the Carbon 4 website, who explain in quite some detail how this carbon budget is actually computed. It's an interesting read up. So let's split this up a little bit more. For electricity, you can see that more than half of it is used at Paranal. So that's for the VLT and VST, Vista, and some other telescopes there. And that I think could easily be replaced by solar power. This is something which ESO is looking into at the moment, which is also being looked into for the ELT, by the way. For purchases, there's a number of issues or a number of contributors that come in here: IT and equipment, maintenance, and equipment. This is essentially products that are bought from other companies. So this is the carbon footprint of other companies, so to say, that is bought partly by ESO. And then for travel, as you can imagine, 80% comes from long-haul travel. So that's mostly from Europe to Chile. that can be reduced. Again, in my view, we can discuss perhaps ideas of how that can be reduced, but it's hard to conceive how this can be completely eliminated if you want to operate an observatory in Chile from Germany. As a third example, I'd like to bring a comparison between two big astronomical conferences, the European Astronomical Society's annual conferences in Lyon last year, the EOS 2019 meeting, and the EAS 2020 meeting that was supposed to happen in Leiden this year, but then took place as an online meeting. For the first meeting, the EOS meeting, well, actually for both meetings, we ran exit surveys that were answered by various people. You can read up the details in the publication that is upcoming. For the first meeting, the essential numbers here, on the first plot, you can see the amount, the emissions broken down into amount of emissions, and you can see that most of the trips actually produced relatively little emissions because they happened within Europe, or let's say very close to Europe, like Israel or the Spanish islands. And this group of people who produced about 50% of the emissions is actually 90% of the people. So 90% of the participants produced 50% of the emission. 10% of the participants, those who traveled from overseas, produced also 50% of the emissions. That is one of the interesting numbers that came out here. And for the European participants at least, we asked, could they have traveled by train, which not yet, but in principle could be carbon neutral if the electricity for the trains is provided through solar power, wind power, and other means. And this is the numbers that you can see here. So the green bars are the travel times that people accepted, or that people actually traveled on the train, and the yellow bars are the travel times that those people who could have traveled by train, that's less than 15 hours, so less than, let's say, one full day of train travel, not taking into account night trains in this case. But for all those who would have been able to reach Lyon within less than 15 hours of train travel, we have these yellow bars. And you can see that most of at least the European mainland, would all have been able to travel by train to the Lyon meeting if they could have reserved a full day before and after the meeting for this train travel, which certainly is not always the case. So we're not suggesting that this is the easy solution. It's just to show that something like 70–80% of the people could have traveled by train if they could have spent the day before and after on the train. Or potentially in the future, if there are night trains, that might be even easier. Now for the EOS 2020 meeting, which was entirely online, we ran an exit survey that was answered by about 35% of people. And we have here a couple more numbers of how long people spent online and how many hours per day they spent online. And from all these, we did a little estimation on how much electricity was required to run the laptops, again with some assumptions, and to transfer all the data through the internet. And with all these numbers, we come to a final number of 588 kilograms of CO2 emissions for the entire EOS 2020 meeting. So for this whole week of meeting, the added emission compared to just living in your house, in your home office, are less than 600 kilograms. This corresponds to a single one return flight from Liverpool to Lyon, last year's conference site. And that is quite interesting. So that means that this year's online meeting, which was by the way the largest astronomy online meeting today, produced less than 1,000th of the emission of last year's meeting. And it was seen as rather successful, I think, by most participants who participated very actively in Slack and other means. So this, I think, is really an option for the future. But there are limits to individual action. Reducing your own carbon footprint by traveling by train, possibly eating less meat and other activities are all good. But in the end, as we are seeing in the COVID crisis, which is reducing emissions by just 8%, although the economy has partly almost stopped, what we need is really system change. We need to find ways to stop burning fossil fuels altogether. Not just you and me using a plastic bag 10 times or not using plastic at all, traveling by train and so on. That's all nice and good, it's a sign. And it's an important sign, I think. But in the end, we need to become active all together to demand from our politicians that we need to have a change in the system. We need to stop burning fossil fuels. And this is why I think astronomers can do actually even more than just, let's say, cleaning up our own business, which is also important for the reasons mentioned before. But we can also lend credibility to the climate movements. And I have a few slides here on what that might mean. So one is we can provide facts, very important these days, and methods. For example, there are still some people who say, well, the temperature increase is just due to solar activity. Well, that's clearly not the case. And there's data that shows that, and we can explain how these data are gathered, how they are processed, how you calibrate such data, and what it actually means to convince people that no, that the sun is actually not the culprit of the global warming that we see. It's really our own production. We can also provide perspective, like in this fantastic image called Earthrise from the Apollo 8 astronauts, that shows Earth against this backdrop of black space, and that really shows that we all belong together, and there are no boundaries as seen from space, and we should all work together for a better future of mankind, humankind. Finally, there's even more perspective that we can provide by looking from further away, and that is this fantastic image from the Voyager 1 space probe that Carl Sagan called the pale blue dot, the one point that you can hardly see, that shows that Earth is really, really tiny in our universe, and this view, this perspective, this feeling, if you really allow it in yourself, that makes you really feel, oh, we should really, really do everything that we can to protect our own planet, because there is nothing around us where we could go to. There's more arguments. We can really say there is also no planet B. We can also not go to Mars or Venus or the Moon or whatever, some other place, or even some exoplanet that has recently been called Earth 2.0 or something. All these planets are not accessible for almost everyone on this planet. They might be accessible for a few rich people. Elon Musk and his friends might be able to go there at some point, but certainly not for you and me. So this is not the solution to our climate crisis. This is a nice dream to have, perhaps for the very far future, but it's not a solution to this problem that we need to solve within the next few decades. And finally, although I'm always a bit skeptical how to say this, there is this psychological effect that says that awe triggers empathy. So if you have an image that is very beautiful or very inspiring, it increases your empathy towards the person who shows you that image, or empathy in general. And of course this is a bit dangerous because we don't want to be manipulative, but it is of course so that astronomical images can be very beautiful, very inspiring, very just wonderful to watch. And this effect to just show the beauty of nature is also an aspect that I think we should use in our communication to tell people, look, we have such a wonderful world, let's give it a little bit more care. Now, this brings me to the end of my little talk. On this very last slide, I'd like to show you some more resources around this topic. There's a grassroots movement called Astronomers for Planet Earth, in which we try to collect information and also provide material, outreach material for astronomers and for astronomy educators. We'd like to invite you all to join this group if you'd like. We have a Slack group and various other activities and materials, please just get in touch with me or anyone else from this group, and it would be great to have you part of our group. Thank you.